neural network is actually very simple. It's just adding and multiplying. The complexity of neural networks is not really the math, but it is more the amount of symbols I will introduce. So if you will lose me later because I show that many symbols, just remember it's just adding and multiplication. Besides that, we will use a few functions. Here I show 3 of them. The blue one, sigmoid, tan-h, and relu. There are many other functions which are used, but they all have in common that they are a bit non-linear. They are different for the negative sides than for the positive sides. And later I will show you how we will use those. So if you remember this, if you have understanding of this, you'll be fine. Okay, so let's start with the basics of a neural network. What do? You predict stuff. Typical example is you have got a small picture with something on it, and you try to predict whether there is a cat or not a cat on it. And what you do, each image consists of pixels. Each pixel is just a value. You normalize all those values, you stack them on top of each other, and you call this the normalized input vector. And this is what you just insert into your neural network. Well, let's do that. And you let the neural network calculate, and it says, yes, it's a no cat. And actually, simple as this goes here, it's also that simple in Keras. In Keras, you just start with your object model. I will later show you how you make that. You use the method predict. You insert your input vector, which I just showed you, and you get an output, a prediction, which is, for example, 1 or 0. So some people think a neural network is a black box, but you can just look at it in it, see what's happening inside. So let's do that. Here we have this input vector again, and this input vector is just multiplied by another vector called the weights vector. And here I depict this with just a number of W's. Those are numbers, of course. So you multiply by weights, and then you add another bunch of weights, this B, this is called the bias weight. And you can write this concisely in vector shape like W times X plus B. And so my vectors are boldface, my scalars are not boldface. So this is the first step. Then what's happening next? You insert this thing in such an activation function. This is one of the functions I showed you the first time. In this case, the sigmoid function, for example. And you get an answer. And you can also write this shortly. This sigmoid function, you can write it as a sigma Wx plus B is your A. And what we've got here actually is one neuron of a neural network. And this is schematically shown as an X and a line and then a circle with an A in it. So here we've got our first element of our neural network. It's this simple. Okay, just to memorize a bit, a legend. So we've got our X, our W, our bias, our sigmoid function, and A as an answer. These are the basic building blocks of a neural network. And from now on, we will just see more of the same, basically. Sometimes just a different symbol, but this is the essential of stuff. I showed you one neuron. You can stack a lot of neurons on top of each other. That's what we call a layer. And this again is a lot of the same. Now I show this with a G, an activation function. This doesn't have to be the sigmoid function. That can also be one of those others, the relu or the tan-h. It's not, it's not that essential. And if you, if you take them all together, you can also write it more concisely like this. These W vectors can be combined into a matrix, large W. So one layer can be written as G, and then large W X plus B, and this is what we call our answer vector. A in square brackets a 1. The answer of the first layer. So if you got, this is the activation function and the weight matrix, answer vector. Those are the new letters. Okay. from one layer, you can already make, or actually one layer and put another small layer next to it. You can already make a neural network, and you can get a predicted output. And that, works as follows. So on this one layer, we can put this A1 again inside this function. It's the same function again. We multiply it by another factor of weights. We add another B. We put it in an activation function, and here we've got our new answer, the answer of the second layer, which is in this case just directly your prediction of 1 or 0, for example. If you don't put it into an activation function, you probably just get a number, and that can be also used if you want a number instead of a classification, for example. So you can choose what you do in the end. Okay, so this is a simple neural network with 2 layers basically, or 1 hidden layer. Of course, you can make larger things. You can stack as many as you want behind each other, and the more layers, the more weights you've got, and the longer it will take to use it to predict something, of course. In the right corner, you see the general formula of each layer, basically. It's an iterative formula. Your answer, your output is dependent on your answer from your previous layer. Okay, so this is the architecture of your neural network. And until now, I assumed that all these weights are just there already. But sometimes you don't have these weights. Sometimes you need to make them yourself. That's what we call training. You need to train your own network, and you do that by optimization. So what you do, you basically try to find the minimum of this thing here. You don't do it by yourself, of course you let the computer do it. And what's this? This I hat you've seen already, that's your predicted value, actually. These Y's, these are the labels. You can imagine this as finding the minimum of a landscape here, finding the minimum of this entire thing. And for a certain set of values, of weights, you will find a minimum, and those weights are the best. And you start with a random point in this landscape. You're randomizing values where to start with. That's some theory. How do you insert it in cicadas? That's pretty easy, actually. You import some layers, dense. That's what's called such a layer, actually. Dense it's called because all nodes are connected with each other. You define your model with a sequential class, and then you just add layer by layer. This number is the amount of nodes you put in. Jeff, I think you will explain this also later, or you can play with it yourself. So, I think now I won't go too deep in it. Okay, then predicting sequential data. That's a little bit a different ballgame. Sequential data, with this we mean time series, for example. That's the main topic of today. But sequential data is also a sentence, for example. So with recurrent neural networks, you can also predict the next word in a sentence. And probably we all have this in our own phone. When you type something, the next word is predicted. And probably this is also a recurrent neural network inside your phone. So we use this a lot nowadays. But for now, let's focus on the time series. First, why is a standard neural network not working so well for time series, actually? Why do we need something more advanced? The answer is that, for example, with sentences or time series also, the input and output length can differ, while regular neural networks always expect a fixed input. Second, basic neural network doesn't share features across different positions. So, for example, in a time series, sometimes you want to share information of this part with information of this part, and that's not so easy to do with a basic neural network. So we need something else. And that's a recurrent neural network. How does it work? So time now is going from left to right. The input to output is going from down to up. So your input is, for example, your time series. That's just these axes. The first point of your time series, second point, etc. So they all go in. But there's also something else which is going in. And those are the A's. Mostly you need an initial A, just zeros. And then in this layer, well, actually two things go in, and also two things go out. That's also different. So what's going in is an A and an X. What goes out is another A and the Y. So what's happening here? For example here, the second A, so A2, well, that's actually again such a formula which we've seen before. It's this one, the G is an activation function. And we've got the previous A, just as we had before. But now there's a new term, and this is the red. This is the weight, which is taking the X value, the time series value, in the information of the neural network. So each A is basically passing information of the time, of the point of the time series, basically, and is dragging it every step along in the entire neural network. So also, very late in a neural network, very far in a neural network, very deep, you can still have information of the beginning. Also, in every step, you can do a prediction already. Prediction based on the first point in your time series, prediction based on the first and the second point together in your time series, etc. And this, this prediction is just actually the same as the formulas we had. Just to compare, this is the blue one is the formula for the basic neural network. You see it's very similar. In the blue I just wrote a G, in green I just wrote the sigma, but those are both these activation functions. So, considering these weights, each X is multiplied by a W, its own W, just another set of numbers which you can train, another set of weights. All A's have their own weights, and all A's to make a Y also have their weights, the green ones. So it's just more of the same, but just in a different architecture. So in this case, every time step there's a prediction, but in this evening we like to do forecast in the future. So basically what we need is, oh, sorry, I just forgot how to implement this in Keras. In Keras you just use simple RNN, and the number of units, that's the number of these circles, the number of nodes within such a layer or a cell. That's important to realize. Okay, so let me continue with this prediction. For us, it's useful to predict the next value of such a time series. And for those things, you will need architectures like this, for example. So you need to predict the next value, t+1. Or if you want to predict farther in the future, you just stack more cells or layers behind it. In Keras, it goes a bit differently. In Keras, it's actually more easy to use the following architecture. So on top of the last one, you just stack another dense layer. And previously, the dense layers were vertically orientated. Now I just rotated it. I rotated it 90 degrees, and out of it, comes prediction. And of course, you can repeat this. You can just stack different layers on top of each other. You make, it looks a bit like a church. You can make nice architectures with it. This is how to implement this in Keras altogether. So what is what? This is important. That is how many units. It's not how many time steps, but this is how many of these circle cells you want. The number of time steps, or the number of layers from left to right, actually, this is determined by the input size of the vector. That's something important to remember. So it's not just entering a number like I want to have a recurrent neural network with a length of 10 or so. No, this is defined by your input. Remember that. For me, it was very confusing the first time I started to use this. Another thing is this variable, return sequences. For these two, it's true. For the last one is false. That's actually whether you want to pass all these y values here or not. So for the lower layers, you want to pass them to the next recurrent layer. But for the last one, you only want to pass this one. So that's what the variable return sequences is telling you. Okay, so again, I think Jeff will explain more about this later. With this recurrent neural networks, there's a problem that's called the vanishing gradient problem. Yeah, that works as follows. If you've got a very long neural network, you get problems with passing information from one side to the other side. And that has to do with the training of your weights. For this, you need gradients. And in front of every gradient, there's a number, and all these numbers are multiplied. And it's quite usual that these numbers are small, between 1 and 0, for example. So suppose all these numbers are 0.1. There's a multiplication of many times 0.1. And you get a very, very small number, which means that the information from here hardly goes to the information way farther. But sometimes you need this. Sometimes you need to transfer information from the beginning of your time series to the end. It's a very long series, or if there are many points, for example. So for this, you need something else, something which can carry information, very long through your neural network. And this is where long short-term memory arrives. This is a solution to transport information, if necessary, from one side to another side in your network. And that works as follows. We introduce another thing to pass in between the layers. And this is the C. It's a memory. Yeah, the memory. It's going from memory cell 1 to memory cell 2. And here you see the formula. It's looking a bit complex, but what it actually means is just this new memory of T is just a combination of the old memory. And of course, you initialize this the first time also. It's a combination of the old memory and a candidate memory. Like this candidate memory is the new information. So every step, it's evaluating, well, shall I just continue with the memory I already have from the past, or shall I update the memory? Because now we just got something which is very important, and I want to take it further. So these are two memory factors, and those are both multiplied by those gamma terms, gamma U and gamma F. And those are called the gates. So gamma U is the update gate, and gamma F is the forget gate. Whether you want to update your memory or you want to forget your memory. And your A is also changing a bit. Your A is another gate, your output gate, this gamma, times the tan H of the memory cell, which is just defined above. So what's this candidate memory? This C tilde. That's just again this this function which we've seen previously also in the recurrent neural network. Just to compare with the blue. So there's just one step in between, and this is the C. But furthermore, it works pretty similar. And then the formulas of all these gates. Those are just also more. That's just more of the same actually. So here's the sigmoid function. I think you recognize this. This is also just another matrix times your previous A, just another matrix times your previous X and your B vector. So it can appear a bit intimidating, but it's a lot of the same. Some people show such a memory cell as this. I always find it a bit confusing. When I saw this for the first time, I thought, well, what's this? Is this electrical engineering or so? Which is electrical circuitry. But some people find it very clear how this works. So you also see memory, this A, and it goes to the forget gate, and then it's multiplied, and you go. That's it. So if you like those, go. Okay. almost done. One last thing. So suppose you've done your predictions, and for example, with a recurrent neural network on LSTM, and here you've got your output. Yeah, it's good to have a bit of a feeling how good it is. So, for example, this prediction. So blue is the time series, and green is a prediction with an LSTM. And at first hand, you could say, "Oh, that's not so bad. And my prediction is almost the same as the real data." But actually, this is very bad, because if I add another model, a very simple model, which is saying the value of tomorrow is the value of today. So this is actually the same data, just shifted by one. You'll see that this red is, well, at some point even better than the green. So this means your green data, your predicted data, is just using, today's data only, actually, or even worse. So this red model, today or tomorrow is today, can be used as a kind of a benchmark. So if you do prediction, forecast with an LSTM, for example, or a recurrent neural network, you can compare it to this persistence model, and judge how good it is or how bad it is. Okay, so far, are there any questions? Yes?
So when would you choose or try a recurrent neural network over a remote profit method that we seen before? Is there like a specific class of problem that it's particularly good at, or?
For time series, I don't know. I don't know if Jeff knows more about. So, for example, for sentences is clear. There, sentences are very non-linear.
Mm-hmm.
They're better to use recurrent neural networks. For time series, it depends a bit. Is there any manual or recommendation when to use a RIMA model, when to use a neural network? Not really, huh? Yeah. Well, then it's up to you to find out what works better.
Yeah.
Okay.
The persistence prediction that after tomorrow is after today, you made it sound as if it's really simple, but I don't really get it. Why is it?
So red is just the same data, but shifted one day.
But if you shift it, it would just be a flat line, right? Or,
so if you shift the red one step to the left, it's exactly overlapping the blue, and the blue is original data.
If you want to predict more than one day in the future, which I think your
for example, this is a prediction of many time steps. Yeah.
okay.
Not clear yet? So this region, so this is training data, for example, and this part is testing. So you're gonna test it, you're gonna compare the predictions. This is a lot of predictions, many points. You compare it to the real data, because you also have the real data.
Oh, that's assuming you include all the data after 100. So.
Yes.
Okay.
Yes. Yeah. So this is all. Maybe I should have written predictions. So this is all predictions, but you still have the real data. So the message here is just check whether your predictions are not very bad. You can do this by benchmarking with this persistence model.
Maybe also one difference would be that you don't have to tune all those parameters. You don't have to know what the frequency is and your seasonality and stuff like that. It figures out itself.
Yeah. An advantage of using a neural network instead of an ARIMA model where you have to tune stuff yourself a bit. Yeah, very true. Yeah. Okay. So this is the theory. Now we go back to the hands-on session again. If Jeff is ready.
So there's I don't know, I've read a lot about RNNs and LSTMs and things like that, but there's a huge difference between actually putting them into practice and reading about them. When you read, they seem actually quite straightforward, but when you're applying them, um, it is hit and miss. It's really a matter of checking out lots and lots of different permutations. And I'll show you how that's generally done. Setting up the data is slightly different too. That's one thing that took me a little bit of time to get used to. So we've gone from a REMA, which is pretty fixed. It's got these certain assumptions that you have to fulfill. We've gone to Facebook profit, where you have some flexibility. You get into the dangers of overfitting though, but you can build a model that's pretty flexible. You can add things to it, take things away. And finally, I agree with the person who said that neural networks are totally open. Everything's, you just say, I don't care what it is, everything, put it into these functions of functions, pop out. So you know, in principle, it's going to outperform anything because everything is a subset of that sort of model. That's the sort of the talk about it, but actually trying to do that in an efficient way is difficult. The one sort of trick I'll show you is that you have to set up your data a little bit differently. So if you have 500 periods of data, you can't run that in one network. It's too long. So at least for normal computers. So what you end up doing is sort of essentially a moving average. So you say, okay, I'm going to take 10 points, and from those 10 points, I'm going to predict the next two. I'm going to move the one over. I'm going to pick the next 10 points, predict the next two. Next 10 points predicts the next two. So this is the way the model sort of built up because you can't do 500 or a million in one. So that's the one sort of tricky thing, and I'll show you how that's done. So with this sort of data, that was just a picture of the original data. So generally, I found that. Oh, please.
Just a quick question. What you're saying about only taking a slice of the time series,
yeah,
kind of implies that if you have a problem with long-term seasonality, that a neural network wouldn't be good for that kind of problem.
We'll pick it up. If it's really short, then yeah, that's going to be the problem, that you're always going to be kind of missing these sort of things. But it has troubles with longer term. That's why most of the examples you see on the internet are essentially using a bunch of periods to predict the next one, next one.
Right.
And that's why you see those.
But if that's where the seasonality is then active, that the neural network will pick it up as well because it doesn't have the context to do that.
Yeah, that's my understanding. Yeah.
Thanks.
So scaling the data is important. That really seems to help speed up the process. All of these sort of functions are available. So you can use, in this case, standard scalars. So I'm using sklearn, scaling the data. In this case, it didn't do much. It just sort of shrank it a little bit. Splitting the data, standard sort of process of splitting it into tests and train. The only thing you have to be careful about is in your time series, you don't randomly split it. You make sure to split it in units, time units. Here's the part that I was explaining about, this sort of creating a moving window to form sequences and labels. So what you essentially do is, in this case, I'm looking 15, I want to predict 15 periods in the future based on 15 points in the past. Now these are things that you can choose. These are, the trouble is when you choose 100 units in the past, so if you want to get the seasonality, then it becomes awfully slow. So if you really want to do these, then you probably want to have access to a bigger computer. But essentially what this is doing is, like I said before, creating a whole bunch of samples. 15, go back 50 and predict the next 15. Move one up, another 50, predict the next 15. That's essentially what this function is doing. You don't have to do that in other sorts of models. Grid search. So, like I said, there are lots and lots of parameters that you have to fit. So, in almost all of these, you'll see some sort of grid search going on. And these are fairly easy to, there are lots of examples around. Screen. And this is actually sort of a sklearn wrapper around it. So this is doing grid search CV, also random grid searches as well. And essentially you're going through, and this is just a small subset of the things that you have to search. So, you know, here you'd put, so for instance, if you were to do it in a, really you'd have like, you know, for your dropout rate of 0.5, for instance, 0.8, you'd have different neurons, inputs. You do different initial modes for the, when it's searching for an optimum, you'd use different optimizers, and you'd go through every single permutation. That's essentially all you've got when you're doing neural networks. Now, it's harder to drop in and drop out layers. I'm sure it must be possible. So for instance, if you put had a, you know, a 0 layer or something like that, something equivalent like that, but essentially it doesn't, and so far, at least in the examples I've seen, it didn't make a lot of difference in the output. But here is essentially the code for creating a grid search, finding the best sort of model. And once you have that model, then you essentially run it. So here's my model, my sequential model, my LSTM layer, a dropout layer, another LSTM dropout, and finally a dense layer. And another tricky feature of neural networks is these seem to be, getting the shape can be sort of a burden. It seems to depend on what sort of structure you're using. But this is sort of for, at least in Keras, TensorFlow Keras, this structure seems to be good. So this will be the structure that says whatever it was. So use 15 periods to predict the next 5. This would be the 15 periods. And down here at the end, of course, you want to have the 5 periods if that's what you're doing. And this will do that for you. So, and then you essentially run this, collect the data, and then you plot and see what's happening. In this case, it's the test. There's clearly a lot more. For instance, you can run more epochs, or you could change your model. This is the test data. It's still very much in front of the, or higher than the training data, so there's still lots of information in this data to learn. So that's essentially it. You get a, this doesn't do particularly well, because again, it's a sort of a bad model, but a quick one. And that's the end of the sort of the talk. And again, all these the Python scripts and the notebooks are available. Would anyone like to use notebooks now? Because we've set up that you can go to the Jupyter Hub and use a notebook. Would anyone like to do that now? Or, no? Need a break? Maybe time for a break? Yeah, good. We'll talk about it. Good.
Okay, so yeah, so these considerations you wrote there,
Yeah.
those are the things you can work on. Yeah. So
How
if
can we
you,
access the notebooks?
if you like to start, yeah, so so maybe it's good to show how we access the notebooks.
Yeah, okay, but you can also access the notebooks on the Jupyter Hub.
Yeah, that's easier, and then everything's installed. So what I did is I essentially set up a, so you have to pick your user, you know, so user 001 and 002, and then you have to, what you have to do, unfortunately, I tried it with Bitly, but that didn't work, so you have to type in this address,
Including the Git pool?
Pardon?
Including the Git pool? Or
Yeah,
just
the whole thing, unfortunately. Hope you're a better typist than I am. And then that will take you to, we'll ask you for your password, and perhaps you could be user 001, 002 if you like, and so forth. Yeah. You can choose your password. Sorry,
I think you can just pick it.
Okay.
Because nobody else pick it, yeah, and this is a pick another one.
Should make it work.
Yeah, actually, that's exactly. That's what I did. Yeah.
Is anyone else trying to get on?
I'm in, but I have no notebooks.
I'm user one. Yeah.
User 17.
Yeah, I don't know why this, sometimes I work in.
Okay. Yeah, I was trying it, but I just, stuff was new, and just felt like 3A, but that's what so I need to get, and I noticed on 3A, no, so I need to get an file first. So I need to do that at some point later. Yeah. Okay, I'll try. User, what was the last thing? How far did it go?
Powerful administrative stuff.
Oh, just user.
Yeah, let's see, maybe use it 20.
Now we have the interesting situation of the data.
That's a good question.
Somehow they will not able to understand.
Dus op de buiten dit is
So basically, this person get reimbursed. However, there are also AWS costs. You have to see what's so we have this funny situation that these days now I just want to request. You can text us, so you can separately pushing is not linked to project cost or the meeting of
I assume so, but I don't know how to check, but I assume so.
Yeah, I can ask.
Yeah, exactly. Okay. No, it's all right, it's all right.
This guy was
Yeah, okay, but
How are you?
And it's like user, the name, whatever has on it. And then make up a password. Hopefully it works. Something is so amazing.
Yeah, exactly. I already did what Spark is not. Since everything is set up.
Yeah, it's.
That's different when you use cases. Now the question is interesting because
Ja, ik zie tijdens die dan nu wel.
Well, I also used to be able to pick a different one.
Oh, that's okay. So it's under. Just mess around with it and, yeah, so I'm
Some turbulence.
Ik kan ook hier. Ja, dat komt. I'm going to. I've got 7 now, so I'm going to go down
Okay, so maybe we should try it another time. It's strange to me, because sometimes it's good. Yeah, we also kind of know. The kidney is good. But not the second time.
Sorry, can I ask you? I was just wondering, is it also get on first to use for the end?
Makes sense. There starts to oscillate and comes up with.
So what you're saying is you do a prediction.
Two samples ahead, and those 2 samples you just write out those 2 samples. Use this as
And the actual observations or the predictions.
predict 2 samples ahead, and you go to the 4 samples.
But using real-time physical or using prediction to prediction to predict 2 things.
Okay, so let's say you use the previous 4 samples to predict the next sample. Right, so my just take the next prediction. Forget about the and then you plus your own prediction and then predict 2 samples.
There's nothing
I guess the alternative is you take more past samples into account.
Yeah, that's another possibility as well. So there's a lot of examples you see that they do, but that's another option.
Natuurlijk kan je wel naar die patiënt sluiten.
Ja.
As well, depending on
I guess you get some kind of also recursive behavior, which somehow is also included. Yeah, observing it, perhaps you don't install the system. Because it's just exploding.
No, that's true. I think you would have exactly the same thing. The coefficient of greater than 1, and you also have to split. So that's what we want you to. You see at the bottom.
Oh, but I also found interesting somehow hourly, yearly.
Yeah.
Audio.
Yeah, I was gonna say that.
Yeah, and then you're really working on. And basically you're looking at
So I think I guess so.
Ja, but also these out of the rest.
Nee, dat is wel, dat is het.
Ja, want
Het is nog steeds. Het is niet meer. Dit is
the
ook veel uit.
encoders here they also try to predict somehow and only prediction error encoded is yeah. I'm not sure it's called out, it's also out of the rest okay, but I'm pretty sure it's the same stuff. So you basically fast samples with yeah, you get your weights. The nice thing about this weight is here also. Also, they start to and then you why you can use it. That's the same. Yeah.
Ja, change code. Ja. Sorry?
Sorry?
Druk een beetje, een beetje. Ja. Lijkt het überhaupt aan het gaan. De packages die op is.
0, 0.
Ja. Maakt de Hensel 6 iedereen aan de eerste hele basics.
But you actually own a car. Lekker. But you set it up.
Main question for you about there's never done it, but loose
Where did you go?
So I don't know, this is limited contact. Worried about it. Proteins. You want to think of a different model to make sure not vary too widely. If you find something that you model in order, check that. The difficulty is Venus is doesn't scale. Not that I haven't attacked thoroughly, kind of naive, very, I can imagine if you get the right term. Yeah, that's also. I'll take a scoop down. No, I actually think I'm going to. Okay, thanks. You know if it's going to be online to review?
I just don't have, yeah, something can happen. Do you want?
No, the video.
Oh, that's not under station.
Yeah.
Yeah, that's just what I want, because someone else has to. So this is my presentation, so your kid. Yeah, sure. That's actually possible.
Thanks very much. This is an actual.
I wasn't sure. I wasn't sure.
No, I think you have a wide variety here. The fact that the audience is fairly chances of stating it, but very quiet. I would rather see a lot of material in little time than too little material in too much time.
Sorry about that, please. Thank you very much.
Oh, good, I'm glad to hear.
Thanks.
Thank you. Could you send you the presentation?
Okay, push it to.
Yeah. The presentation is also be put on GitHub, on this repo. So there you can download it.
Want het zijn altijd hele logische voorbeelden. Ik heb ze vandaag gevraagd. Ik heb ze nog niet. Ja. Wat voor zeker is het?
Marco.
Ja, dat is toch een bedrijf in Amsterdam. Die bij snacken. Net iets anders. Ja, ook interessant.
Ja, en ik vroeg me af hoe jij die benchmarks gebruikt, of dat wel de juiste manier is. Want met die benchmark kun je vanuit dus eigen data die had een model, had die data niet een beetje een valspel.
Ik heb wel eens
Je model stopt met predictiviteit. Zelfpredictiviteit.
Dus je hebt zelf ook
Precies. Als je dat naar de benchmark ook gewoon gewoon vergelijken. Zoals iemand in de aanzet.
de benchmark, dat is gewoon eigenlijk hetzelfde.
Maar jij deed het zeg maar tot 300. Als je dat net als je model. Je model als je je benchmark ook had, dan werd het daarna steeds stap voor. Jij pakt nu gewoon je eigen data en die doet gewoon 1 of verder. En ik weet niet of dat een hele goede benchmark is.
Maar stel je stapje voor stapje, dat die lijn die ik zag, dat is eigenlijk dat we ons moeten aanpakken. De lijn die ik zag, nou ga je stapje voor stapje. Dag bij dag, dus een nieuwe predictie maken. Eigenlijk wat ik aanraad. Je zegt gewoon, ik had een hele lijn gegeven. Ik wou gewoon los datapuntje voor datapuntje, dus een nieuwe predictie. En na 100 extra predicties ik zelf trekken die lijn aan. Dan heb je dus wel, die dag heb je een nieuwe predictie. Ja, je zet het hier zeg maar, een nieuwe voorspelling. En dan wacht je bijvoorbeeld dat het uitkomt. Dan doe je weer een voorspelling. En als je dan gewoon deze voorspelling doet van de laatste dag, stapje door stapje doen. Dus elke dag, dus vandaag de temperatuur. Zeg morgen, graden is nu, dus 9 graden. Zo, kun je morgen is het ook 9 graden. Ja, precies. Morgen en overmorgen is het ook 9 graden. Snap je, dat wat ik weet. Morgen is het 11 graden.
En dan precies, dat weet je ook, het model niet.
Ja, als je dus stapje voor stapje wel.
Dat was het precies wat we toch
Ja, kan je ze wel gebruiken. Elke dag, 1 dag.